start recording. So when the question comes up, and maybe you'll have to answer this someday from someone who says, hey, what are you doing in school? Ooh, learning about circuits. What is a circuit? What is a circuit? Like, uh-oh. Now I got to explain it. I understand it, but I got to explain it. Now I would say, as you're looking at it and reading the definition, you might even be reading this definition and going, I still don't get it. So I'm going to try to help you get this. All right, but take your time, write it out. We'll set up the 1, 2, 3, 4.
It wasn't a question.
These are the 4 things made up of the 4. These will have definitions, not questions. Sorry about that. Definitions.
Yeah, for sure. So number 1.
And they'll yeah. You guys were like, well, I should have put a question 5, all of the above.
Yeah.
Yeah, okay. If there were questions, that's the first time that's happened, so good. All right, these are not questions. These are the 4 things that make up a circuit. And so I'm going to put some definitions around it. Really not a big definitions. It might just be one word to establish what it is that you're focusing on when you're trying to understand this. So a circuit, a closed path, through which current, and this is where I want to kind of help. This is why I put that. And you don't see this a lot, especially in school, where instead of using current flowing through the circuit, which is correct, by the way, that's the correct way to understand it. Current flows through the circuit, pushed through by voltage. We can get into the physics side of how electrons move, but we're electricians. Do we really need to know? Maybe, yes. In many cases, yes, if you go into the DC side of things, because that behaves a little bit more like what we learn with positive, negative, and electron movement. AC behaves a little bit differently, so it's almost better to understand AC just from voltage. If I have a closed path, what does it mean to be a closed path? And we'll use the power sources. So the first thing that we're going to need is a panel. So this is a power source, or a source of power. Now, usually we have panels. That is where we're going to find things as to whether or not circuits are on, breakers live in there. But sources of power are not always that. So I'll put a couple more just to kind of get your brains into the world of what power sources can be. Transformers as well. And control, I'm going to add panel here as well, just for an easy word. They're called motor control stations, but we don't have to use all that. Control panels. Right, these are all places where you would find the source of power. Right, the source of power. The thing that brings in voltage. So, if we are trying to figure out why there is no voltage in the circuit, all right, we'll get into continuing to describe the definition of circuit itself, but if I'm trying to figure out why there's no voltage here, I have to know where these power sources are. These are the things that bring voltage, and yes, current, but we're electricians. We measure voltage. If you're ever trying to figure out why something's not working, if an outlet doesn't have power, and you're trying to go, why is there no power at the outlet? You don't turn to current. You don't turn to amperage on your meter and go and check to see, hey, do I have this closed path that we keep hearing about? You check voltage. You check voltage at the outlet. You check voltage at the connections to the outlet. You check voltage back at the panel. You go into all of these things to see if voltage is living there, not current. All right, that's why, again, I have this. The other thing we need, of course, we're going to need conductors. Here, I'm just going to put wires, all the various different kinds. Size wires, we're going to get into. This is all code that gives us how to define a circuit as far as what the wires are going to need to deal with. And we'll get into, which you should have already talked about, continuous and non-continuous. But like I said, you were kind of just thrown continuous and non-continuous in code A. Today we're going to put it together, or this module I should say, we put it together a little bit more focused. As far as loads go, all right, loads are anything that uses energy. All right, I want to make sure people understand what a load is, because you're going to hear load a lot. All right, the load in the circuit. All right, bring power to the load. Check if the load is working. What we're talking about is the thing that is using the voltage that we've sent into the circuit. So loads are, just to put some examples of ones that are definitely going to be around, which is lights. All right, definitely lights. We have motors. We have heat sources. Things like heaters, heating elements for restaurant equipment, heating elements for heating a building, heating elements for heating up water in machinery, all kinds of heating sources. These are all the things that we use electricity for. Well, what about outlets? Outlet is not a load. The thing you plugged into the outlet is a load. So think about the things in your kitchen, for example, that you plug into outlets. A blender, motors. Toaster, heat sources. Right? So these are all air fryer, heat sources. Right? Think about all the things we plug in. They're kind of all there. There's only one other one, and that's sound, noise, horns, and not music. So these are low. I almost like to remove sound because it kind of gets us into a different world. So these are about what I have. And you can think of other things that we plug in. All right, refrigerators, kind of a heat source because it goes into compression of, trying to think of all these. You know, we can even put cooling systems as well, HVAC. So we can talk more about loads as they go on. All right, but again, the thing I want to make sure you understand is not the outlet. The outlet is not a load. Right? Because when we talk about branch circuits, a lot of times we talk about the circuit with just the outlet, not the thing that gets plugged into the outlet. So we have to, well, we'll get into that, but we'll have to do some calculating around things that will be plugged into an outlet as we're setting up a circuit. Right? If that makes a little bit of sense, not so much yet. Again, we'll unpack that a little bit more as far as loads go. And last but not least is protections. So here we have breakers or / fuses. Don't forget the fuse. We live a lot with around the breakers, you know, just in common every day, you see more breakers than fuses. But as we start to go into commercial and industrial, you see more fuses. That's not a V, that's a U. Sorry about that. But every time I talk about the protection of a circuit, I'm not going to say breakers or fuses. I'm going to say, and you should learn it, OCPD. If you need to write that out, and it is a definition you learned in code A, over current device. Very good. I was waiting for that last one.
Oh.
Yeah, you got lower as you were. You got lower as you were saying it. I was like, yeah, go with it. All right, over current protection device. Over current protection. These are three things. You'll learn more about this in code D as you get into short circuit and faults, more faults. But there are three over current situations, and that is a short circuit, a ground fault, and an overload. Too much amperage in the circuit. And we'll talk a little bit about those because we are going to talk about GFCIs that protect from some of those. And we will talk about overloading because we are going to learn how to size breakers for a circuit, which have to account for somebody plugging too many things into the outlet and kicking off the breaker. All right, and so a circuit, getting now into the final of this, is a completion through all of this. All right, the complete circuit, and now I'll use, we'll go to this panel. We'll talk more about this panel for a second, but I'll just use it for my design here very quickly. I will leave a breaker, a power source with protection. To make it easy, I'll just put a switch here. All right, this switch will go to a load of some kind. Just to describe this as an easy circuit, let's just say a light bulb, but of course we wouldn't just have one light on this circuit. We'd have many lights if we're talking about, a bunch of outside lights or something like that. Living room lights, so there's never ever one light on a circuit in most cases, but I don't need to worry about that too much because we're just describing the circuit right now. And then we got to get back to the neutral bar. All right, there's my neutral bar. So this is a circuit. Circuit is the completion of all of that. From the source back to the source through the neutral, leaving the power source through the hot, arriving at a load, and then from there heading back to the neutral. Now the position, we can get into status of the position later on as you go into the control side of the courses, but this is an open circuit right now because that switch is in the open position. Now, if I close this switch, now the circuit is in the closed position. All right, just a couple of terms that you'll get more into later on, but it's good to start to already use the proper language. Open circuit, closed circuit versus on and off. We can say on and off. That's okay. Everybody will understand you, but open or closed is a little bit better because an open circuit is a not complete circuit. A closed circuit is a complete circuit. All right, I'll pause there. Any questions? So far so good, just as far as... All right, going back because I skipped something. I'll get to this one, but before we leave circuit. So now we understand a circuit has to have a source of power, something that's a conductor getting that source of power to a load, and then the load heads back on the neutral side. Circuit is protected by the breaker. Wires have to be sized to the load that will be energized. That's our main concern. What's getting plugged into this thing? Is it 5 amps? Is it 300 amps? Different size wire, different size breaker. So now let's talk about what this article is describing, which is a branch circuit. Right? A branch circuit, and again, you do have this definition. I think I'm getting this almost straight out of the code book. I may have changed a word or two, but a branch circuit specifically is a circuit that originates at the final breaker in the circuit. I'll explain that a little bit more. But basically, starts at a breaker and ends at where the load is connected. And there's where I've kind of reworded it a little bit. If you look at the exact definition in the code book, it's not that one. But it's using most of these words. So a circuit that starts at a overcurrent protection device, fuse or breaker, and ends where the load is connected. All right, and specifically, the final overcurrent protection device. And I'll explain that. All right, go ahead and write that down. If you need to, if you got this, again, if you got this, no worries. All right, and as you're writing this and writing the fact that we originates at a breaker and ends at a load. The next article that we're going to look at after 210 is 215. 215 is on feeders, which is the other circuit. There are only two types of circuits: branch circuits and feeder circuits. Now, feeder is kind of divided into feeders and service. We'll talk more about that when we get into that article, but these are the only two types of circuits that there are outside of motor control. We're just talking about our standard circuits, breaker panel, outlets, motors, and things that get plugged in, and then the power that comes into the building. So the power that comes into the building, all right, the outside transformer, for example, to describe a house and the wires are coming down, we have our weatherhead coming into this panel. These wires here, this is a circuit being brought to us by the utility company. This circuit is a feeder circuit. All right, now in this particular case, it is also a service, meaning it is bringing power into the building, so we call that the service. But these are feeders, and this is a feeder circuit. Now, inside we have a panel. Remember, the feeder circuits just came into this panel. 2 wires came in, or however many we have, 3-phase and all that. Now we have a breaker in here. Doesn't matter the size of the breaker. And we send a wire out like we just did in that circuit. Let's bring that back with our load over here and heading back over to our neutral. This is a branch circuit. Starts at the breaker. We'll talk about final here for a second, sorry. And it originates, ends at where the load is connected. Now, when we say where the load is connected, here's where, instead of that, we could have just an outlet. Meaning, and now think about the outlets in your house that aren't doing anything right now, that don't have anything plugged into them. This is not technically the load. This is just an outlet. So, where the load is connected. So if it's an outlet system where you have to plug this load in, then that's the branch circuit from the breaker to that receptacle that then you will plug something into. Now, if we're talking about more machines, machines go from these 2 different systems, but power usually just goes into the machine, like wires just go into the machine and they get terminated in there. All right, terminated means you land those wires on a terminal block inside the machinery. So there are all kinds of different ways in which wires end up at a load. So that's why I described it like that, where the load is connected. Now I'm going to describe another situation coming from that same panel. Now we have, let me just bring that one back. I'm going to make it real short. No need to be that long. We have this breaker and this, let's just put 20 amps here. So we have a branch circuit here. Breaker, load. But here's another situation coming from this same panel, right? Let's say this person has a garage and inside the garage they have a sub panel. Another panel in that property. This is the main panel, that would be called a sub panel. So let's say there's a breaker in this same panel. Let's say it's a 60 amp breaker now. Let's say now we're sending 240 over to this panel, right? So we have A phase and B phase going into this panel. And now these wires land at their own main breaker in here. These are not, or this is not a branch circuit. This is a feeder circuit. So this is why final is the important part of that definition. Because now let's say, for example, from this one inside my garage, I got a 20 amp breaker in here feeding an outlet that whatever, I got my compressor plugged into. This is now the branch circuit. Because final breaker over current protection device to the load is the actual definition. This circuit that was coming to this is the feeder circuit. So don't get bogged down. What I want to make sure you're understanding about a branch circuit is it doesn't just start at a panel and end, or whatever circuit leaves a panel, is a branch circuit. No. Right, it's not just any circuit that leaves a panel is a branch circuit. Specifically, where is it going? If it's going right to where the load is getting plugged into, either terminating inside the load machinery or an outlet so that you can plug something in, then that's a branch circuit. If it's going from like this situation, from this breaker to that other breaker, which will be the definition that I'll give you when we get to Article 215, originates at a breaker and ends at a breaker, or OCPD to OCPD. That's a feeder. Now, today is not a conversation on feeders, so we don't have to worry about it, but just to describe it. All right, questions. It's got to be something. Can't just be me talking. All right, but good. If this is all making sense, good. I mean, it should, I guess, in a way. You guys are all coming in from having talked about a lot of this stuff. So if it's making sense so far, good. Now let's jump over into the article. And this is why I said we got to kind of know where we're at in the circuit system to now understand the rest of this. Because if I just start with multi-wire branch circuit, it's not going to make sense immediately. So let's read A. All right, that's what we're jumping down to, 210 multi-wire branch circuits. And you can read it now, and maybe it might make a little bit more sense now, but I'm still going to break this down a little bit more. So it says there in the general A note, it says branch circuits recognized by this article shall be permitted as multi-wire branch circuits. So good so far. All right, let's just understand this sentence. It's saying that those branch circuits, like I just showed you, leaving the breaker panel and ending up at the load, we can actually make them multi-wire branch circuits. Okay, got that so far. Now, if you don't know what a multi-wire branch circuit is, that's what we're going to talk more about. But the next sentence says, a multi-wire branch circuit can also be considered as multiple circuits. So multi-wire circuit, multiple circuits, that starts to get a little bit confusing because it sounds like almost the same thing. What do they mean by multi-wire versus multiple? Don't worry about the except as portion of this. This gets into another article that we don't need. But the next part is important. Again, don't worry about the except, but all wires, all conductors of a multi-wire branch circuit shall all start in the same place, in the same panel, in the same power source. All right, that's what this is saying. But the way the code writes it is, all conductors of a multi-wire branch circuit shall originate from the equipment. Notice they're not saying the panel. They're saying from the piece of equipment that has the overcurrent protection device. There are all kinds of different types out there, especially when you start getting into the world of machinery. There's disconnects, there's, like I said, motor control panels, there's equipment shut-off systems that have overcurrent protection in them. So whatever piece of equipment, now for the most part, I'll describe this as a panel as we talk about things, because for the most part, that's what we'll deal with, but that's what and that's why they're not saying it specifically from a panel. Just wherever all of these wires get that power from, they all have to originate from there. All right, so 3 things that we're going to talk about now. 1, what is a multi-wire branch circuit? 2, what is a multiple circuit within a multi-wire branch circuit? And 3, as to the originating, because it actually gets caught in the next part of this, which is turning all of those conductors off, or the ones that we do shut off. All right. 1 second. Okay. There we go. I had lost the definition. Sorry about that. All right, here's the next part, which is what is a multi-wire branch circuit. So here's the definition. Let's first write that out. Writing is always best. Of course, again, I'll provide this stuff for you after the lecture. But writing is always best. We memorize as we write. We don't have to 100%. All right, so again, now as you're writing this out, I'll just kind of catch us up to where we're at. We understand what a circuit is. We've got an idea of it. Complete from the power source back to the power source. A branch circuit is originating at a panel or some power source. Again, we'll mostly call that a panel. Probably 99% of the time a breaker. And then ending up at a load. So a multi-wire branch circuit is this. A circuit, branch circuit, consisting of two hot conductors with a common neutral, and important that we understand, we'll talk about this, when the neutral is used in that multi-wire branch circuit. Examples of voltages are these: 120, 208, 120, 240, and now as we get into industrial, you'll get into the higher voltages of 277 and 480, which I'll have all three of these examples. All right, I'll have all three of these examples with a panel. Now, just as a side note, as you're writing these voltages, these are created by transformers. So, when it comes to residential transformers, they are 120, 240. Commercial buildings, industrial buildings, and commercial buildings will have that higher one. Just some extra.
Do you know any firefighters from California that just moved to Chattanooga?
Oh, you know a firefighter that just moved out here?
Yeah, I was just wondering if you knew of it. A bunch of firefighters that I know actually moved there.
Oh, really? No, I don't know anyone in particular, no.
A whole group of them.
Oh, wow. Yeah, a lot of people are moving here. We're getting, it's good for the housing market. Now that I own one.
How much is the mortgage?
It's not bad. I bought this house for 240.
Wow.
Okay, he also hasn't told you that he's in the middle of nowhere. That's a pretty
No,
big...
Chattanooga's not in the middle.
Yeah, no, it's peaceful, man.
Thank you. We are 2 hours from Nashville and Atlanta.
Oh, nice.
Yeah, we're near the Smoky Mountains. We're good. We this is a small major city. It would be like a Pasadena,
Oh.
you know. But then imagine that outside of Pasadena is not everywhere else. It's just nothing else.
Yeah.
Yeah. It's a lot of sticks around us for a while, and then you get to a very small town.
Sounds like a peaceful life.
It is quite.
Yeah. What's the other one? Other fucking city, Tennessee?
Knoxville?
Yeah, that one too.
All right.
To get profile.
You get profile up there?
here, man.
All right, so we're good with this note. What is a multi-wire branch circuit? It means it's going to have two hots and a neutral when we use the neutral. Again, I'm going to show you all these examples. So there's the key to this system now. A multi-wire branch circuit is going to have two hot conductors, but also, again, we're going to pick this up as well. A multi-wire branch circuit can also be multiple circuits. So let's get into that. All right. So first of all, this is a panel. Now you should be able, on my side from here, it looks like you can see everything in fairly good detail, meaning the colors of the wires should be translating just fine. The terminating points of the conductors as well, so you might be able to identify a few things if I ask some questions, right? Hopefully. And so when I ask the question, if you can't see something, just let me know. But first, how do I want to, let's ask it this way. If you're looking at this panel, what would you guess the voltage of this panel to be?
240.
120, 240. All right. 120, 240. Now, is this because this is the one you're familiar with, or are there some features here that are kind of indicating something?
The neutral only has two wires coming into the line on the top.
Okay, so we have A phase and we have B phase.
Yeah.
And we have the neutral here. Does everybody see that? It is black as well, not identified. You can't really see it too well. You may be able to see a little bit more there, yellow. This is aluminum conductors, used a lot for residential service. Just cheaper. I guess also there was like a boom in the 70s and 80s, I guess, maybe. Or a particular set of years where aluminum was used a lot. These days, new construction, I think everybody's using copper. Does anybody see it? So, I mean, this is where I want to lead the question too. So if we're looking at 120/240, if we had to guess, is this a residential, commercial, or obviously not industrial, just given that we're at 120/240, would you guess more residential or commercial?
Residential.
All right. Now, are there any features that you're seeing there that indicate this might be residential?
It's messy.
Yeah, first of all.
Yeah. Number two looks like a handyman did it.
Is
Yeah.
You see Romex in there?
I know.
Very good. That's what I was looking for. Romex. Very good. Yeah, you can see the Romex. I was hoping you can see it. Yeah, there's a little bit of Romex in there. So Romex is usually residential. So very good. This is a residential panel, 120/240. Just to complete all those numbers, 120 on A phase, 120 on B phase. And so as you look at the panel, a few things to understand about the panel is all of those breakers, the two on the top, the first row, these are A phase, the two on the next row are B phase, and then it goes in that order from there. A, B, A, B, A, B, A, B, A, B, A, B, all the way down. All right, so meaning 120 over here, 120 from B phase. If we were to measure between both with our meters, then we'd get 240 volts. Now we have two types of breakers out there. There's single pole breakers and two pole breakers. All right, a single pole breaker, in fact, let's pull them up just to make sure everybody, I'm guessing you've already seen these. Yeah, here's a good, I just pull up the internet. If you can't see something, let me know, but you should be able to, just to zoom in a little bit better on that. These are actually two single pole breakers and one two pole breaker that you're looking at right here. That one is a two pole breaker. All right, it has one joining connecting bar across both of the phases, meaning when I on or off this, it's A and B at the same time. Now you look at the description there, Eaton, don't worry about that, but 20 amps, 120, 240 AC single phase. 10,000 KA, which you'll learn more about next module. That's the short circuit interrupting rating, and yes, 10,000 amps wants to go into this circuit in the event of a short circuit, which is crazy. Yeah, I know, but that's why that 10 KA is 10,000. So, and there's 20 amps. So there's a difference here. That 10,000 and that 20 amps, these are both protecting the circuit, just two different things. This 20 amps is just the standard rating for the circuits, for a 20 amp circuit. Now, the one next to it is a single pole breaker. You'll see that 10,000 there as well, by the way. This is a single pole breaker, 20, and you can see just one handle. All right, here we have two handles, one bar. Now, here we have two handles, but no bar between both, meaning independent, independent. This is called a tandem, T-A-N-D-E-M, tandem breaker. All right, you'll learn a little bit more about breakers and overcurrent protection components like fuses and breakers. As you get into Code D, you'll get a lot more of these in hand in front of you. But just I will talk about these because I do want to represent things that you'll see. Now, what this little breaker does is it gives you the ability to turn one of these into two of these. Now, it's important that we understand this because there's going to be a next note that comes up when we disconnect, which is right here. at the same time, simultaneously. All right, now we're not going to look at this just yet, and I'm going to recenter my, but what they're going to want us to do is they're going to want us to shut off the hot conductors. We can look at it now, actually. Let's actually look at it now, everybody. And we can actually go ahead and highlight this. It completes itself up here in this top part. And it's actually worth mentioning now as we go into the next bit of this, which is each multi-wire branch circuit. And again, I haven't fully described the multi-wire branch circuit yet, but I've already said, going back over the note 1 second, more than one ungrounded conductor means 2, 3 as we get into 3-phase. That's what the more than one is referencing. So what this note is saying is each one of those wires, ungrounded conductors, each multi-wire branch circuit shall be provided with a means that will simultaneously turn off all of those hot conductors that you are using in your multi-wire branch circuit, simultaneously meaning at the same time at the panel. Again, at the point where the branch circuit originates. Again, we should just call it a panel. Meaning, if I'm using more than one hot in my multi-wire branch circuit, then I have to use one of these breakers, either, sorry, let me reposition, either the double here with 2 independents that can be shut off at the same time because they both live in the same housing. This one that has the bar across from it, they sell a little bar that you can add to this one to make them both shut off at the same time. This one already has the bar. 2 pole breakers come with it. Or use 2 of these side by side, and again, they do sell a bar to join 2 of these together. But if you're going to take up a lot more space that way than if you use one of these, right? Because these count for 2 of those. So now you have 2 of these taking up 2 big spaces in the panel, where you can use one of these. And now again, you can put a little bar between both of those, just the same way that one is set up, and shut them both off at the same time. All right, now we're going to talk more about why they want us to shut them off at the same time. Again, this is the things that we try to learn more about, why these things are done, but that's the main thing as we start to go into this. The hot conductors have to both be shut off at the same time. Meaning if you're looking at this, I'm going to have these breakers either together in, 2 pole A phase, B phase, or one and then one right next to it so that I can side by side join these 2 together. Or, and I don't see one on this panel, use a tandem, and again, where one breaker has 1 and 2 shut-off points. All right, these are the style breakers that we can use here. Okay, so let's get into a multi-wire branch circuit. I'm going to erase that. Well, actually, let's keep that there. It's good to keep it as a reference. So here's an example of a multi-wire branch circuit, but not a multi-wire branch circuit. So I'll use it this way, and I just want to make sure I have good space here. 1 breaker, right? And let's say we just pick up the breaker right under it as well. All right, we'll do that where we take 2 big breakers and make them. We won't use the tandem. It's just for the editing here as far as me drawing stuff out. Not going to look good. All right, so we have our breaker, and we run our hot conductor over to, and I'm going to draw this out as an outlet, neutral, hot, ground, and yes, I have the hot right now on the wrong side, but don't worry about that. It's just the way the drawing works itself out. So another circuit, another hot conductor heading over to another outlet. And so far, we have a multi-wire branch circuit. All right, where we have multiple circuits. All right. So we have our breaker going to outlet. Now, neutral, and here's where, going back over to my note, a common neutral. What is a common neutral between both of these? Well, a neutral in which, leaving the neutral bar, I bring over to this outlet, splice however we wire this up, junction box and all those good things, and provide it for the other outlet as well. This is a multi-wire branch circuit with a shared neutral. Now, here's what's going on. All right, let's break down what's going on. We have A phase, B phase. Actually, it works out that I picked correctly. This one is A phase, this one is B phase, meaning that's A phase and that's B phase. So we have 120 volts on the hot, 120 volts on this hot. Now, these two are outlets. This is not a load, but this is the point where the loads plug in. So let's put some loads into this. Let's plug in whatever, a load of any kind. We'll just put an L here. And let's say when I plug this in and turn it on, when that thing is operating, again, it could be a light, it could be the blender that I just turned on, or the microwave, or this is the circuit with the refrigerator just cycling on through, or these are the lights to the house, whatever. When I power this thing up, it draws, what we call it, 10 load amps. All right, the amperage that we measure on the circuit when the load is on. Now, to this outlet, we're going to plug in another load. All right, we're going to plug in another load. And let's say again, when I turn this thing on, whatever it is, it draws 5 amps. Now, can anyone tell me how much amperage I should expect on this neutral? First, there's that. The neutral, of course, has amperage. And this gets to the disconnecting simultaneous. And I'll talk about a thing that just happened to me 2 weeks ago when I was doing a side job. But how much, can anyone tell me how much amperage that neutral should have?
15
All right, we got 15 over here.
or 20.
Does anyone have a different number? Not 20.
That's the amperage code.
There's one other possible number,
The neutral?
15.
15, because what I'm assuming you are doing is one load has 10, the other one has 5, and, right?
Yes.
But is it just 20? Because that's how much is in the breaker.
Say that one more time.
Is it 20 because that's how much you're starting with in the very
Okay, that's a
beginning?
good question. Let's actually start there. That's a good answer, or that's a good question to have at this point. So the breaker, let's say this breaker, and both of those breakers are 20 amp breakers. What the 20 amp breaker is saying to this circuit is the most you can plug into each of these individual outlets is 20 amps. If you plug in anything more than 20, I'm going to trip. So, and this is why, again, getting back to this add-on to my definition. Breakers aren't providing current for the circuit. They're just making voltage available at this outlet. Current happens in the circuit when you plug something in and turn that thing on. And now the circuit will have whatever current is being generated by the load. So the breaker is just set up to protect this circuit from too much amperage being plugged into it and causing fire, really, because this wire is going to feel the heat from too much amperage. In other words, let's say whatever I plugged in, or I plugged in multiple things, you know, in people's homes, they plug in as much as they want. 25 amps. Well, this 20 amp breaker now is going to trip. It's going to open that circuit up and cause, at the very least, power to shut off, the load to stop putting all that amperage onto the circuit, and things to shut off.
So then purely hypothetically, if we have an electric car and that wire gets really hot all the time, could that be because the panel isn't?
No. Things get hot. That's a normal thing. That's a normal thing. Here, I want you to do an experiment. And this is what you can do. All you can do at your house. You can do at your house. No, don't worry. Nobody's going to get hurt. Here's what I want you to do. I want you to take your charger from your phone. I want you to plug it into the outlet. Don't plug your phone in. Just plug it into the outlet. And I want you to leave it in there for as long as you want this experiment to prove this point to you. You can do this for 10 minutes, 20 minutes, an hour, 3 hours, doesn't matter. Touch the block. You will feel no heat. Plug your phone in and give it 20 minutes and then go touch the block. There is now heat on that. That little thing is a transformer, by the way. because current is now flowing through the circuit. So wires get hot when current is flowing through the circuit. So it's okay for you to sense heat on wires. That is normal. Touch any extension cord that's being used, it's hot. Breakers during operation get hot physically. Go ahead, say that again.
But hypothetically speaking, let's say that charger will continuously turn off because it says it's too hot, which is not normal.
The charger won't do it. The breaker will trip. The charger will go until it burns down. The breaker has to be the one that shuts the circuit off.
You have an old panel that doesn't trip.
Now, if you have an old panel that doesn't trip, therein lies fires. This is why we have fire departments.
Yeah, this is a new house. I couldn't. Yeah.
New house. Hot conductor.
But
Yeah.
moved it too.
The wire is hot. First of all, the wire is hot on an extension cord. That's not a worry. We don't like extension cords, so that's not. If the wire is hot in the panel at the breakers or all that, then that's a worry. That's a worry. You have way too many things plugged into that circuit, maybe, but heat is normal. Heat comes from current. That is okay. All right, again, I have a 20 amp breaker. I can ride as close to that 20 amps as I want. There is an 80% rule that we try to keep to. All right, there is an 80% of this 20 amp breaker that I want to stay at. So about 16 amps is good to load on a 20 amp breaker when we have a continuous load. More on this when we get to that, because it is going to come up in this article when we have to size a breaker for a circuit. So, but that's what that means. The breaker is only the protection, not the amperage in the circuit. The amperage, as you guys are saying here. So let's place ourselves in this circuit. By the way, this 15 is wrong. We'll get to that.
10?
What is it?
Is it 10?
Nope.
What?
You're going in the right direction, by the way. Can I hit
You're
that?
right.
5 amps.
That's why I said there really is only one possible answer. Either you're adding this or you're subtracting it. Either you're saying 10 plus 5 or you're saying 5 minus 10 or whatever.
Also,
10
it's 59%.
So it's actually 5. Yes, that is the correct answer. Measured anywhere along the circuit because we are AC. Either I'm measuring the neutral at the panel with my amp meter, or I'm measuring it over here at this outlet with my amp meter, or at the other one. It does not matter. AC is that way.
Is that because it's a 15 amp receptacle?
No. We'll get to why this number is. By the way, does anybody know why it's 5?
More voltage, less amps?
No, not Ohm's law.
Yeah, more voltage, less amps.
Then I have no idea.
No, that's okay. Again, it's just, but I also want to get to this. If I measure this with my meter, I'm going to measure 10 here amps. If I measure this circuit along the line anywhere, I'm going to measure 5. But then when I measure the neutral, I measure 5 amps as well, because here's the job of the neutral. All right, this is the job of the neutral. The neutral's job is to carry the unbalance between loads.
Why doesn't that second breaker have 10 amps on it as well?
Because whatever we just plugged in is only drawing 5 amps.
Oh, okay.
Yeah, these are hypothetical numbers.
Right.
All
Okay.
right? Now, by the way, okay, so we'll get into another question that has come up as well, which is, well then why does the neutral have to be number 12 in this circuit if it's only dealing with 5 amps? Well, because if I happen to disconnect this today, now there's no balance. There's nothing to counterbalance that 10. So now the neutral is carrying 10 today. The amperage on the neutral changes throughout the day and throughout, whatever's on and or off. If, again, by the way, now I disconnect everything. I disconnect this load from the outlet and the other, then there's 0 on the neutral. If I plug into this outlet something that has 18 amps, now there's 18 on the neutral. At the same moment, you plug something in that is whatever, 6 amps. Whatever you've plugged in, minus. The unbalance of 18 minus 6, 12 amps. So this is why we make sure that the neutral is the same size as the hot conductors, because potentially a lot, potentially now something else comes in and balances it. Sometimes it's at 0, sometimes it's at full capacity, sometimes it's at medium, whatever the circuit allows. But what you should understand is, don't even worry about the loads plugged in, whoops, is the neutral is going to carry the unbalance of both. Or the unbalance between these two independent circuits, where you can plug whatever you want into this one and whatever one to this one. They're independent of each other. So the neutral is now dealing with whatever is left over, the unbalance of the load. No, so, oh, sorry, I meant to say. Now imagine this situation, which I actually had it happen to me this weekend, or 2 weekends ago. And I actually saw it on one of these Instagram little things where the question was asked, why does this neutral have, why is it arcing? So I'll explain here a situation. Let's say I have something plugged into this outlet and it's generating whatever I plugged into this outlet, when I turn it on, 12 amps. Again, this is called load current, meaning the amperage being generated by the thing you've plugged into the outlet. That's causing the heat. The 12 amps is heat. It's literally equal to heat. Now, the other outlet has gone bad somehow, right? Somebody plugged in something here. It had a short in it, killed this outlet in the bedroom somewhere. These outlets, by the way, are not in the same rooms to each other. This one's over in the living room. This one's over in the bedrooms. Or in one office, the other office. Whatever scenario you want to put this, but they are not even living near each other. They don't know each other, just sharing this neutral. So shorted out this outlet, so now this outlet has to be replaced. So what am I going to do when I go to replace this outlet? Well, I'm going to turn this breaker off. But here's what happens to those 12 amps. Where are those 12 amps going? They're heading back, but they're also here at this outlet. So if you leave the other breaker on with something still plugged into it, generating load current, this is the one that, when you were talking all that safety stuff, kills us. If you go to now remove this outlet, you take off this hot conductor, this neutral is, you shut off the hot, this neutral is live right now. It has 12 amps on it, has 120 pushing it, and if you ground yourself in this system, now it's going through you to ground. The neutral is the most dangerous conductor in the circuit because it has that load current on it, which can be accumulated from having shared the neutral in different circuits. So here comes the code book. By the way, when I was a young electrician, this was the way we did it. But here comes the code book now. I don't remember exactly when they changed this, but I know it changes, or maybe I'm misremembering this, as we sometimes tend to do with memories. But it says now simultaneous. So, for example, and this is what happens a lot, this is why you have to be careful. And I think this is where that Instagram video kind of showed up as to asking the question. Let's say someone can't put this breaker next to it. There's just no space in the panel. The only other space is down here somewhere. And now I've run this hot, or whoever ran the hot to this breaker. They're sharing, you don't know that they're sharing the neutrals. You're about to get into this circuit. Right? You're going to go and, shut this one, whichever one. You're working on that one. You're shutting this one off because you're going to work on this one. Or actually, I had to load on the other one, so you shut this one off. And again, you don't know that neutrals are being shared because they're not next to each other. They're not set up to simultaneously. There's no way now to connect these two together in the panel. So the thing you have to do is, and people don't do it, they get lazy, they'd have to move this around. What they would have to do is start to, like, maybe for example, take this circuit here and move it to the bottom. And then you have space to put your other breaker next to that one. But people don't do that, and this is where we get hurt sometimes on that line, because someone's sharing the neutral here.
Is there any way to know that before you start putting your fingers in places?
Measure the amperage on the neutral. Now here's the thing. I would never think of that. I would get shocked by that neutral.
So that's a code violation.
That is a code violation, and it is also a grandfathered in situation too, maybe, where back in the day they used to do it, now they don't. And so you have this from old circuits that can come back and bite you somewhere. So the best thing to do is always check your neutral for load. You know, run an amp tester. If I'm in residential, I'm suspecting it. If I'm in commercial or residential, I'm suspecting it. Industrial we'll talk about, but I'm suspecting it, especially in commercial, because they do this with lighting systems in commercial circuits all the time. And those lighting systems in commercial buildings are not 120, they're 277. So that is a real bad hit on that neutral.
Damn.
It is a rough hit on the neutral. If, again, you leave one circuit on the other ones, because now they accumulated too. And it also depends on how much amperage is out there. That's why they say it's not the voltage that gets you, it's the amperage. If there was nothing on this, then that neutral would have nothing. You would. Now, how did it happen to me? I was saying it was happening to me. I was working on a EV circuit, like I was putting in a car charging station for someone. And I was at the neutral bar putting in my circuit, and the neutral, another neutral slipped out. Somebody didn't put it in well, slipped out, and it arced. So when I went to put it back in, it was arcing. Meaning, this is crazy, but this is the reality. If I get that neutral, and I don't put it back into the neutral panel, if I touch that neutral, grab the copper and ground, I'm getting a massive hit of shock. If I take that neutral and land it on the neutral bar and touch the neutral bar to ground, nothing. Because the panel is grounded. So I am no longer. I'm resistance. They don't care about me. Because now the neutral has a path to ground that is 0 or very low resistance in ohms. I'm just this big giant ohm resistance thing that it's like, why would I even want to go that route? Seems like a terrible situation for me. So, neutrals have load. Be careful on that. All right, we'll wrap this up here in the next few minutes because I only have 2 more things to describe. That was the big meat and potatoes of it. Understanding that the neutral in some circuits is shared. Now, here's another. I'll use this panel now. And I just had this picture because I wanted to show you the difference between a commercial and a residential with 2 A phase and B phase, because I remember somebody said, well, I only see 2 wires. So I was going to hold that in my pocket for now. Here are 2 wires too.
That's a nice setup.
Oh, there's the difference, right? Nice setup. Another key feature is this neutral is white, meaning it was identified. Commercial feature.
It's still 120, right?
Obviously 277.
It is still 120. Very good. Very good. Still no.
He said it was obviously 277.
No, I'll show you that one. This will be that one. Well, this will be the 3 phase. All right. This is the A phase, the B phase, and the C phase. No, this is also 120 because, and we'll get into this next. And we'll look at this tomorrow. It's actually right here. Identification of these. How do we identify a grounded conductor, grounding conductor, the ungrounded, and from that, this red, all right, there's a couple of red conductors here, are key features of low voltage, what we call 120, 240 as well. This one's 120, 240 as well. All right, now, 120, 240. I'm going to go back here for a second, and there's 120, 208. That's an odd number, but it is this one. This is also, hey, key features red, right? There's my key feature of 120. Also the blue. And you can see them up here on the A, B, and the C. Red, blue, identifying features. I'll give you these notes tomorrow so you don't have to worry about this. I am going to fill you in on all of this 120, 240, and 480 colors. And 277. We'll get into all that. But just to show you that. This is now a 120 3-phase 208. This is what you have in the building. 120 208. 3-phase. So it provides you the ability to have motors connected if you needed to, but commercial 120 usage for offices. offices, computers, and so think about the school, for example. We need 208 in the school for, our elevator's hydraulic, but air conditioning system in the school, HVAC, needs 3-phase for these large industrial, commercial air conditioning systems on the roof. We need it for our 3-phase motors in the motor control lab, so we need 3-phase. But the most that we need is all the outlets for all the computers and all that, so we need 120 more than we need. Industrial is a little bit different. I'll show you an industrial one tomorrow when we get into the color coordinating. But last but not least, I just wanted to show you here, and using this 3-phase one as an example of a multi-wire branch circuit, I'm going to go back here for 1 second, that does not have a neutral. Because as I said, common neutral if applicable, multi-wire branch circuit can also look like this one, for example, is a 3-phase breaker. It has A phase, B phase, and C phase. All right, I don't know where it's going, but wherever it's going, it's to a 3-phase system. Now, the ones that you will talk about will be motors. So let's already even just bring it in. Here's our little motor, and there's all kinds of stuff that gets in between this motor. We're not just sending wires straight to a motor. It'll have a control system, which you guys will get into, how this motor turns on and off. This could be an elevator, this could be a whatever. But this is a 3-phase system. So now let's think about it, and here's where we'll wrap things up. A few minutes, give me just a little bit more of your time. This is a load motor. Let's say the load on this motor is 20 amps. When it turns on, it generates 20 amps. This is what that means. It means if you measure A phase, 20 amps. If you measure B phase, 20. And C phase, 20. First of all, yes, 100% of the time, unless we're in some other physics world, it'll be even throughout all 3 phases. Some things can get in the way of that, like one wire being a little longer than the other one can throw it off by a few, but not a lot. So we'll just say even. So what does this mean? Balanced. 3-phase motors, which you'll find when you get to the next module, will have no neutrals. All right, there's a couple of other things like this, water heaters and dryers, the old ones, but there's no, sorry, wrong color that I like to use, but there's no neutral going to this. Right? No neutral setup going to that. Because of why? Because of the balance. What is the neutral doing here? 20, 20, 20 means 0 would be on the neutral, so no neutral involved. Now, this is a multi-wire, more than one ungrounded conductor, multi-wire branch circuit. It's going to a load branch circuit, not another panel somewhere. So it fits all of it. It's a branch circuit, it's a multi-wire branch circuit, but it has no neutral. Going back 1, 2, I erased it all, but there's where it was. It's on video. Multi-wire branch circuit with a neutral. All right. Now this one, no worries about turning it all off at the same time. It has one handle, like the 2-pole. This is a 3-pole and has one handle. So these shut off all at the same time. Big worry again is that neutral carrying some kind of load where a breaker wasn't shut off simultaneously at the same time. And it goes into explaining that on the neutral side here. I don't want to rush this, so I am going to talk a little bit about this where we'll start tomorrow, just kind of breaking down. See, as I said, we weren't going to get too far today in all the ways that I wanted to talk about branch circuits, and multi-wire. But we'll start here tomorrow at identifying